Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to show you how to solve a problem that involves the masses and the fractional amounts of different isotopes. And so in this problem here we have natural rubidium, and they're giving us the average mass of natural rubidium. And so we're going to use that. But first we need to remind ourselves what the general equation is of how to find or how to calculate either masses or percent mass or percent abundance or the average atomic mass of an element. So how do you calculate the average atomic mass of an element when you're given information of the isotopes? Well, it's this equation right here. So it's the atomic weight or average atomic mass of an element is equal to, it's going to be the percent abundance, the percent abundance of isotope number 1 multiplied by the mass of isotope 1. And then you're going to add to that the same thing. So if we have another isotope, it would be the percent abundance of isotope number 2 multiplied by the mass of isotope number 2, followed by whatever other, if I have whatever other isotopes I have, I would keep adding. So if I have a third isotope, then it would be the percent abundance of isotope number 3 multiplied by the mass of isotope number 3, and so on, dot, dot, dot. So that is the general equation for solving this sort of problem. Okay, so we have 2 isotopes, so we're not going to use isotope number 3. So we're going to have a percent abundance of isotope 1 multiplied by mass of isotope number 1, and then percent abundance number 2 multiplied by mass number 2. So we don't need any more than that. So we can erase this to save us some room. Looks like we got some blue purple left over. Okay, so we've got the mass of rubidium-85. So they're giving us rubidium-87, rubidium-85. Those are the 2 isotopes of rubidium. They're giving us the average atomic mass of rubidium. So that's our average weight here. So the average atomic mass, that's this. So that would go here. They're giving us the mass of rubidium-85. So that would be 1 mass. So if we would say isotope, mass of isotope 1, let's say that this is 85 and then this is 87. So they're giving us this, they're giving us this, and they also give us the ratio of the atoms. So the ratio of the atoms of 85, rubidium-85 to rubidium-87 in natural rubidium is this fraction here, this ratio here. Okay, and then they want us to calculate the atomic mass of rubidium. So they want of rubidium-87. So they want us to find this mass here. But what they're not giving us is the percent abundances. So how do we solve this equation without percent abundances? Because we have 2 unknowns. Actually, we have 3 unknowns, mass of 87 and the percent. So we would need like 3 equations, or unless we have another way of solving this. But the key here is this fraction here. So they gave us the ratio of rubidium-85 to rubidium-87, and this is the ratio. So we got to use that. So how do we use that? So this is how. So they're giving us the ratio. So this is, oops, let me get my, all right, so they give us 85, so rubidium 85 over rubidium-87. And that ratio is 2.591. Well, that's the same as 2.591 over 1. So we could do this. So 2.591 over 1. So what this is saying that for every one rubidium-87 isotope or atom we have, we're going to have 2.591 rubidium-85 isotopes. So if I have one of these, then I'm going to have 2.591 of these. So that's how we want to understand this. So we can figure out, well, if this is our ratio, if I, for every one of these, I have 2.591 of these, then if I add that together, I get a total, right? So if I add 1 for every one rubidium-87 that I have, I also have 2.591. So 2.591 of these. So if I add these together, then the total would become 3.591 of each. So for every one of these, I get 2.591 of these. If I add those together, I get a total of 3.591 atoms. So now I have a total of these atoms. I have each a part, and now I can write a ratio with the part related to the whole. And if you remember from percentages, you need a part divided by a whole multiplied by 100. That'll give you percentage. So using the fraction that they gave us, we can get a whole from there, assuming if we only had one atom of this, we would get how many atoms of rubidium-85. So for every one atom of rubidium-87, we have 2.591 atoms. And so if that was all we had, then the total of that would be 1 plus 2.591, give us 3.591. So that's our total. So now we can use this to find a percent abundance. So here, this is our rubidium-87. So the rubidium-87 would be the part, that's 1. Now the whole is 3.591. And so that would be the fraction, part over whole. Now all we need to do is multiply that by 100 and we get our percentage. So let's calculate that really quickly. And so 1 divided by 3.591 times 100 equals, and we get 27.847. So 27.84, 739%. I'm adding other digits there because we don't want to have a rounding mistake. So here, this is the percent, and this would be, since we're starting with 1, that is rubidium-87. So this is rubidium-87. Okay. So that's the percent abundance of rubidium-87. We could do the same thing with rubidium-85. Take 2.591 divided by 3.591 multiplied by 100. That could give you the percentage. Or since we only have two isotopes, so that means that it's going to be out of 100. So we could just subtract this from 100 and we get our answer. So if we take 100%, subtract out the 2.784,739% for the rubidium-87, that'll give us the percentage of rubidium-85. So I subtract and I get 72.152. So 72.15260. I'll stop there, percent, and that's rubidium 85. Okay, so now we have our percent abundances. So now we can take those percent abundances, plug them into the equation here. We have everything we need. We have our atomic weight, which is this number here. So we'll go ahead and put that in there. So we have 85.4678, 4678, and that's grams per mole. And then that's going to be equal to percent abundance of isotope number one. Isotope number one is 85. So 85, that's going to be 72.15260%. And then we're going to multiply that by the mass of isotope 85. So they're giving us the mass of isotope 85, 84.9117. So 84.9117 grams per mole. And then we add to that the other part. So here we have a percent abundance of 87. So that is this percent. So that's going to be 27.84739%. And then that's going to be multiplied by the mass of 87. We don't know the mass. That's what we're going to find out. Mass of 87, isotope of mass 87. So now we have everything. Now, the one thing we need to be careful of is this here. It's not percent. We need to make sure that we're dividing this by 100 because we want our fractional. It's the fractional amount of the isotope. So it's going to be divided by 100 to get the fractional amount. So it's the fractional amount of the isotope. So to get the fractional amount, we're dividing the percent by 100 to go back to the fraction. So here, the fractional amount, which we could have gotten if we just did this here. So if we did that, we put that fractional amount in there, we could do that. That would be the same thing. So that we could put that fractional amount in for that percentage there. So that would be instead of 27, actually it wouldn't be, it would be this fractional amount here. We could put that fraction in there. And then for the other one, it would be 2.591 over 3.591. That fractional amount would go here. So that's an important thing to remember. So once we get this, or you could use the percentages and divide by 100, but that would be an extra step given the problem. Okay, so what we need to do is make sure we divide this by 100, divide this by 100, and then you solve the equation. So this ends up becoming 85.4678 grams per mole. And that's going to be equal to 0.7215260 multiplied by 84.9117 grams per mole. plus, and then this is going to be 0.2784739 multiplied by the mass of 87. And then if you multiply these together, let's go ahead and do that. So 0.7215260 times 84.9117 equals, and you get 61.2659. So you get 61.2659 grams per mole, plus this part here. So you get 0.2784739 multiplied by the mass of isotope number 87, and that's equal to this. So all we need to do then is subtract this from both sides. So we're going to subtract this from this side, and we'll subtract from this 61.2659 grams per mole. And so if we subtract that, so 85 minus this, so 85.4678 minus that equals, and you get 24. So this is going to be 24. I'm going to write it over here. So you get 24.201.201. I'll throw an 8 in there. 8 grams per mole. And now that is going to be equal to this part here. So that's going to be equal to 0.27847. I'm going to just stop it at the 7. We don't need that many digits. That, and then multiplied by the mass of 87. So now all I need to do is divide both sides by 0.27847. Divide this by 0.27847. I divide both sides by that. And then I get mass of 87, mass of 87 by itself. And so then the answer is going to be this number divided by 0.27847 equals, and I get 86.9099 grams per mole. And so that would be the mass of isotope 87. We need to check our sig figs. Notice that the significant figures they gave us here is 1, 2, 3, 4, 5, 6. So that's 6 sig figs. They gave us here 84.911. So that's 6 sig figs. And they gave us this number here, but that's a ratio. So that's got a number of sig figs. That's going to be infinite. And so, the number of sig figs is going to be 6. So if we do our calculation, if we do that, we would just keep 6 sig figs. So it's going to be 869099. Let me check my answer really quick. And that's a 0. So 0 following that. So we don't need to increase this. So the final answer is 86.9099 grams per mole. And you can see that mass is very close to 90 97, which is what you would expect for the atomic mass of the isotope. So that's rubidium-87's mass. I hope this was helpful. If you like this video, please hit the like button, share the video, subscribe to my channel, put a comment in the comment section. Let me know what you think. And if you have any questions, let me know if you like the video. So thanks for joining me and have a great day.